Alright, so we're going to take another look at some algebra that we would have done last year with quadratics, primarily with expanding and simplifying. So if you remember looking at the different forms of quadratics that you saw last year, you would have seen standard form, which looks something like y equals ax squared plus bx plus c. Okay, you would have seen vertex form, which we looked at a bit last unit, so the a bracket x minus h squared plus k. Okay, and you saw something like factored form, which had y equals some a value, and then there were two brackets. So maybe coefficients on the x might have something like x minus s, x minus t. Okay, something along those lines. And you looked at how to move between the different forms. So one of the things you looked at was how to expand and simplify quadratics. So you can move from something, let's say, in factored form into something in standard form. Okay, so we're going to review how to go through that today. So let's say we had in a situation like this before. You have 2x minus 1 times x plus 4, and you want to expand and simplify. So you probably would have done a few different methods, and depending how you were taught in grade 10, you might have a different approach for this. So one way you might have been taught was to do something called a distributive property. So the distributive property means, if you think back to grade 9, let's say we had 3 times bracket x plus 1. Well, you would expand and simplify that by multiplying the 3 by everything inside the bracket to get something like 3x plus 3. Okay, and the same principle applies here, even though it's a binomial in this first bracket instead of having a single coefficient or monomial in front, like in this case when you have 3. So taking the exact same approach, you could take 2x minus 1 and multiply it both by the x and by the positive 4 in the bracket. So you get something like x times 2x minus 1. Okay, and then plus 4 times 2x minus 1. Okay, so again, you're distributing that 2x minus 1 by multiplying it by each term in the second bracket. So then you could simplify this further by doing x times 2x to get 2x squared, x times minus 1 giving me minus x, 4 times 2x giving me 8x, and 4 times minus 1 giving me minus 4. And then by collecting your like terms here, you'll notice that you have minus 8x and plus 8x here, so you're going to get 2x squared plus 7x minus 4. Okay, and that's a perfectly valid method to use. It can get a little bit tricky, at least messy to write out algebraically because there's a lot going on, a lot of expanding and simplifying. So instead of using the distributive property, you may have seen a way called using arrays. I'm going to do this exact same problem using arrays, just to show you how that works. So if you want to expand and simplify this using arrays, what you would do, because we have 2 terms in this bracket and 2 terms in this bracket, you would set up a 2 by 2 array, like so. Okay, and let's say we put 2x minus 1 along the top, and the second bracket, x plus 4 along the side, and fill in each box inside the array using multiplication. So let's say here we have x times 2x, you get 2x squared. X times minus 1 gives me minus x, 2x times 4 gives me 8x, and 4 times minus 1 gives me minus 4. You'll see this essentially going to do the exact same thing that we do over here. I still have all the same terms, 2x squared minus x plus 8x minus 4. And I would just collect my like terms again. So here I have 2x terms and 8x and a minus x. I wind up with 2x squared plus 7x minus 4, just like I did before. Okay, the nice thing about using arrays is it's a little bit more visual, and it's probably a little bit easier to make sure you don't miss a term if you have arrays, because you have to fill in every single box in the array. Now, you also may have been taught a method last year called FOIL, so F-O-I-L, which you may remember stood for first, outside, inside, last. So I'm not a big fan of that method for reasons I'll talk about on the next slide, but just to remind yourself how that would have been done, let's say we take the 2x, well, basically the same question as before. Okay, we would start by multiplying the first term of each bracket together, so the first term being 2x and x, so we get 2x squared. Then we would multiply the O for outside, so the outside term, so 2x and positive 4 to give me positive 8x. Then you would multiply your inside terms, so in this case a minus 1 and x, to get minus x. And then L would stand for last, which would be the last term in each bracket, minus 1 and minus 4. And again, you'll see you get the exact same answer as you did all the other methods. Now, the reason I don't like this method, even though it does work in this situation, sorry, that should be a 7x, it only works with a binomial times a binomial. Okay, you'll see when we move on to the next slide over here, when you get a more complicated example, you see this is a 3-term polynomial multiplied by 4-term polynomial. FOIL doesn't work, so you can't just multiply the first term, the outside terms, the inside terms, the last terms. You won't get the right answer. Every term needs to get multiplied by every other term in the other bracket. So the reason I don't like FOIL is because it only works in this situation. So I would suggest if you learn FOIL to try to make sure you use another method. I would strongly suggest using arrays because it's a nice visual way of seeing the multiplication, because the distributed property can be a little bit more cumbersome in terms of how the algebra gets written out. But again, if you were taught FOIL, it definitely works with 2-term, so binomial multiplied by another binomial, but it doesn't work for everything. So let's try and transition away from that. That's something you did last year. Okay, so there's another example here, again a 3-term polynomial by a 4-term polynomial. There's a few strategies you can do. I told you arrays was nice because everything was sort of like visually laid out for you. And some things you can do to make sure the arrays is even easier so that your like terms are always along a diagonal like they were up here. You'll notice that our like terms here, the x's are along the diagonal. You can always ensure that's the case by arranging both polynomials in standard form or descending order of the powers. And potentially if there's a missing term, you can add a placeholder. So let's just say we had the equation x squared plus 4. Well, to make the array a bit easier, we could write this as x squared plus 0x plus 4, which add an extra row to our array, but would make the like terms a little bit easier to see. But again, that's something we can use potentially make it a little bit easier, but hopefully you don't find it too bad even without using those tricks. So here's a more complicated example, and you'll see right away, those of you who like FOIL, it won't work here. So we have a 3-term polynomial multiplied by a 4-term polynomial, and the only thing that changes here is I'm going to set up a larger array. Okay, so I'm going to let you try this on your own. What I'd like you to do is fill in every box in this array using multiplication, so by multiplying the 2 terms on the outside, and then try and collect your like terms to get a final answer. I'll do the first one for you. So up here in the top left corner, we have 4x cubed times 3x squared. So just a bit of a reminder how the exponent rules work. So let's first deal with the coefficients. 4 times 3 gives me 12, and x cubed times x squared, if you're multiplying powers of the same base, remember from grade 9, you would add the exponents. Okay, so x cubed times x squared would give me x to the exponent 5. Okay, so that's that box done for you. I'd like you to take a minute and fill in the rest of the boxes. So pause the video when you're ready to check out the answer. You can push play. Okay, so you can take a look at the answers here. Check every box in your array to make sure it's been multiplied through correctly. They haven't made any mistakes with the multiplication or with the exponents. So once everything's all done, remember you want to try and collect your like terms together. So you only so there was no placeholders required here because every term in the polynomial is there. Every polynomial is already in order of descending power. So you'll see that all your like terms are along diagonal. So it shouldn't be too bad to pick out your like terms. So see, we have 12x to the 5th. And then we have all your x to the 4ths along here. So minus 3x to the 4th and minus 20x to the 4th gives you minus 23x to the 4th. You'll see your x cubed terms, 18 plus 5 plus 8 gives me 31, and so on and so forth. So you have minus 2x squared minus 30x squared minus 21x squared give you minus 53x squared. 35x and 12x give me 47x, then just one constant at minus 14. Okay, so again, you can imagine this being very, very complicated to try and multiply out, remembering every single term that you multiply by every other term. It'd be very, very easy to miss a term. With an array, everything is nicely visually laid out in front of you, so you can hopefully not miss any terms. Okay, and you can also imagine how this would be used in the distributive property. You'd have to take this first bracket, 3x squared minus 5x plus 2, and distribute it through the entire second bracket. So you'd have 4x cubed times the red bracket minus x squared times the red bracket plus 6x times the red bracket minus 7 times the red bracket. And you can do that. I'll leave that for you as an exercise to try for yourself, but you can see that that would potentially be a little more cumbersome in terms of the algebra being written out, so that's why I recommend using arrays. Okay, so with that in mind, let's try a few more complicated examples to see if we're on the right track. So here we've got 3x squared plus 1 times bracket 2x squared minus 5x minus 7. Okay, so I'll let you try this one on your own. The only thing I'll say is this would be a good opportunity if you like having all your like terms along diagonals to try using a placeholder here. So in terms of when you set up your array, you have one option to do the standard way, which is just 3x squared plus 1, and then 2x squared minus 5x minus 7. And that would work, but if you like having all your like terms on diagonal, you can try it this way, where you add an extra 0x row, because you notice that there's no x term in this quadratic. And again, you'll get the same answer in the end, but all your like terms will be on diagonal, which might make it easier at that point. So you can try either one, and when you get an answer, push play, and we'll go through it together. Okay, so you can take a minute and check your arrays, and you can see the difference between with what would happen if you use a placeholder or not. So in either case, your first row and your third row should be the same, but you'll notice here when you go to collect your like terms that you have your x to the fourth term here, your x cubed term is here, your x squared terms are not on the diagonals anymore, there's one here and one here, then you have an x term over here and a constant term also. Okay, so again, just becomes a little bit trickier to find your like terms and put them together, but you will get the right answer in the end, just to be a little bit more careful. If you use the placeholder here, you'll see what happens. Even though you add an extra rows of having 0x cubed, 0x squared, 0x, which doesn't actually change your answer, it seems like it's extra work, but when you get down to the very end of it, you got your x to the fourth terms here, your x cubed terms will be along the diagonal right here, okay, and you've got x squared terms on that diagonal, and so on and so forth. Here are your x terms, and then of course your constants. So again, either one will work. It's just a matter of whether or not you want your like terms to be a little bit easier to see. So either way, for your final answer, you should wind up with 6x to the fourth minus 15x cubed minus 19x squared minus 5x minus 7. And again, the only simplification that has to happen here is that really you're putting your x squared terms together to give you minus 19x squared. Okay, so let's try another one. Okay, so this one, again, same idea, except you'll notice here that now we have some subtraction going on and we have a bracket being squared. I will tell you the most common mistake I see when it comes to multiplying is saying that 3x plus 5 all squared, and what they do is they just square the first term, square the second term. It gives you 9x squared plus 25. This is absolutely wrong. Okay, remember that when you multiply something by itself, that's what squaring it is. So 3x plus 5 all squared is really just 3x plus 5 times 3x plus 5. So this needs to be expanded out using an array or distributive property. So be very, very careful about that. Don't make a mistake doing that. So your next line here is going to be 3x plus 5 times 3x plus 5. Okay, and then you're going to subtract whatever 2x minus 3 times 4x plus 5 is. So my suggestion to you, remember if you're using BEDMAS, multiplication comes before subtraction. Ignore the subtraction for now. Do this multiplication with your arrays, then do this multiplication with your arrays, and then worry about subtracting them. Okay, so I'll give you a chance to do the expansion of the arrays first, and then when you finish that step, check it out, and then we'll go through the last step together. Okay, so you can check your two arrays here. You should get 9x squared plus 30x plus 25 from the 3x plus 5 times 3x plus 5. And the other multiplication should give you 8x squared minus 2x minus 15. The thing to be careful about here now, when you're subtracting, remember that you're subtracting this whole multiplication here, so you have to keep your final result here for the second multiplication in brackets. So this minus sign here you're going to distribute to every single term inside that second bracket. So in slow motion what you wind up with is still your 9x squared plus 30x plus 25. That doesn't change. When you distribute your negative 3, you wind up with minus 8x squared minus negative 2x, which is plus 2x, and then minus negative 15 or plus 15. Okay, and then you can start collecting your like terms. So 9x squared minus 8x squared is x squared, and then we get 32x, and then 40. Okay, so again, a little bit more complicated, but remember, do your multiplication first and make sure you apply your subtraction to every single term, and you'll be fine. Okay, one last example, and this one's a little bit trickier. You'll notice here we've got 3 brackets multiplied together, and a lot more going on over here. So I'd like you to try this on your own, see how far you can get, and we'll run through the answer together in part 2 of this lesson. Okay, we'll see you over there.